everybody, and welcome to this week's Lunch with the Scientist. Dr. Elinor Martin is an associate professor in the School of Meteorology at the University of Oklahoma and an OU co-PI of the South Central Climate Adaptation Science Center. The research team she leads aims to understand climate variability and change, with a specific focus on precipitation variability across the Americas and the tropics. So with that, I'm going to go ahead and welcome in Dr. Elinor Martin. So thank you so much for joining us today.
Hello, thank you for having me.
So we always like to start our Lunch with the Scientist with our scientists kind of giving a little bit of background about how they got into their chosen field. So with that, I'm going to go ahead and turn it over to you.
Okay, thank you so much. So as you said, my name's Elinor, and I work at the University of Oklahoma in the School of Meteorology as a professor and faculty member. And I work mainly in the areas of climate variability and climate change. So in the beginning, I have always loved the environment in all kinds of different forms. I like the air, the water, the soil, rivers. I can remember getting a soil quality testing kit from Santa when I was 8 or 9 and thinking it was the coolest thing ever. And there was this really big event that happened in the UK. So I'm from central England in 1987 when there was this huge storm and it caused a lot of damage across the south of England. You can see that in some of these pictures here. There's a forecaster who said, we're not going to have a hurricane. And then there was this big storm that wasn't a hurricane, but it had hurricane strength winds that caused a lot of damage. And I think that event played in my mind because I remember it. And I eventually decided that I wanted to learn more about the weather and do meteorology. And this is a picture of me when I was a toddler in my Wellington boots and umbrella out in the rain. So it's kind of almost destiny that rainfall and precipitation is what I wanted to learn about. And when I found out and really decided meteorology was what I wanted to do, I learned that it's really important to do a lot of maths and physics. So I took as many maths and physics classes as I could when I was in school, and that set me in a really good position to go to college and learn meteorology and eventually go to graduate school. So I'm going to kind of explain my little journey to get to where I am now, because it sort of ends up going in a circle. So I did my degree in meteorology from the University of Reading, which is a university in England, just west of London. And as part of that program, I spent a year in Oklahoma studying. Here's me graduating with my friends from my degree. So I spent a year doing a study abroad here and really enjoyed it. So I decided I wanted to learn more because I didn't feel like I knew everything yet. And so I went to graduate school in Colorado and did this degree in atmospheric science. I got to enjoy the snow and the mountains. And then I still felt like I wanted to know more. But I got more interested in climate rather than weather. So I moved to Texas and I went to Texas A&M University and I got my PhD there. And after that, I spent 3 years in upstate New York as a research scientist, looking at climate in Africa. And then quite unexpectedly, I ended up as a professor at the University of Oklahoma. So I studied abroad here. I traveled to all these different places and got all of these different educational experiences, and then got back as a faculty member here at the university, which is really fun and really unique. And I get to talk about and learn about the weather and the climate globally while living here in central US. So being a meteorology professor has a lot of different parts to it. So on the right-hand side here is a word cloud that comes from my website, pretty certain, and from my CV. So you can see it's my name, Martin, and these are some of the words that are most popular in the things that I do. So you can see precipitation, climate, science, research, variability, university. So these are kind of things that you start to see that are common in the work that I do. So in my research, I think about climate variability, which we can think of as the wiggles, the ups and downs in the climate, the warm periods, the cold periods, the wet periods, the dry periods. I also think about climate change, which is the long-term changes in the climate. And then I really focus on precipitation, so rain, snow, and ice. And in addition to doing research, I teach the university students here. So I teach classes like an introduction to atmospheric science for freshman students. I teach a class called Managing for a Changing Climate, where we're really kind of hands-on to find solutions, practical ways to deal with changing climate. And I teach a class for graduate students as well called Climate Dynamics. And in addition to all of those things, I also do a lot of work here as the associate director for the undergraduate program to improve our degree program, to make sure our students are really well trained and prepared for careers in the field moving forward, as well as doing lots of student events, being part of professional societies, even more things than that. So it's a lot of fun, and I get to do a lot of different things, which is great. So what is climate science? And really the key here is to understand the difference between weather and climate. So weather is the state of the atmosphere right now. It's short term. Is it cold? Is it wet? Is it dry? Today, it's actually a little bit cold here in Oklahoma. It's cloudy. We had a little bit of rain. That is today's weather. Whereas the climate is the long-term average weather conditions. So it's the statistics of the weather over a long amount of time. So we can express this in different ways. People often say climate is what you expect, right? We expect it in the summer, but weather is what you get. That doesn't mean you won't have a cold day. Or climate is your diet, weather is what you're eating right now. The other example here is climate is your playlist, all of those songs that you have on your phone or your computer, but weather is the song that's playing right now. So you might have a mixture of different things. So I'm really interested in how these two interact and really thinking about this climate scale. What will our climate be like in the future, and what controls what our precipitation is doing in the long term? So we can look at how the climate has changed over the past, so since 1880, by looking at how the temperature of the land has changed. So what this graph is going to show you when I press play is it's going to show you the temperature every month from 1880 all the way until 2019. And it's going to show a blue colored bar below the line if it was colder than normal. And it's going to show a yellow, orange, or red bar above the line if it was warmer than normal. So when I hit play, it's going to move through these months a bit. So we can see in the 1800s, some years were cold, some years were warm. As we move into the 1900s, again, maybe we're getting a few fewer cold years. In the 1920s and 30s, there were a lot more orange reds. In the 40s and 50s, again, not many cold years anymore. In the 60s and 70s, even fewer cold years. Now we're really seeing some big lines, some really hot temperatures and months. And in the 2000s, again, we can really see there's almost no months anymore where it's been colder than normal. Every month has been above average. And this tells us that our climate has been getting warmer and it's been changing over the past, and we might expect it to continue changing in the future. And this is just another way of visualizing the same thing. So these are called the climate stripes, and they've become very popular. And so each of these stripes going up and down the page is a different temperature for a specific year. So this goes from 1860 until near the present, and this is for the global temperature. So when you see the blue colors and the darker blue, it means it was colder than normal. See the red and the darker reds, it was warmer than normal. So we can see over time, we've gone from blues into more oranges, and now we're seeing those really dark red colors. So there's a lot of reasons why this has been happening, and our climate can change because of natural things that are happening. These are things like how the Earth orbits around the sun. So if the shape or the orbit of the Earth change, then that's going to change our climate. Just like other planets have different climate to us because they're a different distance from the sun. Our climate can also change if the strength of the sun changes. If the sun gives out more energy, then it's going to cause us to get warmer. And the sun has gradually been getting stronger, but this is over billions of years, not over a 100-year time period. Our climate can also change if we have something like an asteroid impact the Earth, right? Which we know has not happened over the past 100 years. But there's also factors that are internal on Earth that can affect our climate. So things like where the land is and where the oceans are. Volcanoes that erupt can impact our climate. The ocean and how the shape of the ocean and how the currents move impact climate, as well as changes in what the atmosphere is made of. So our atmosphere is mainly made of nitrogen and oxygen, but if we start to change what our atmosphere is made of, it can impact our climate. And we know now that humans have been changing what our atmosphere is made of. And we've been doing that by adding greenhouse gases, things like carbon dioxide to the atmosphere. So here on the left-hand side, this is time before 2005. So where you see it say 10,000, that was 10,000 years ago. And we know how much carbon dioxide was in the atmosphere then by looking at things like ice cores, capturing little bubbles of air in them. So for the past 10,000 years, the carbon dioxide in the atmosphere has gone up a little bit, but it's been between 250 and 270 parts per million. But recently, we can see this line has shot way up really quickly to well over 350 parts per million. And on the other side, since 1960, we've been measuring this carbon dioxide from a special observatory in Hawaii on Mauna Loa. And so this shows since 1960 how much the carbon dioxide in our atmosphere has been changing and going up. So now, most recently, we're up close to 420 parts per million. And we're able to identify that this comes from things like burning fossil fuels, like coal and gas, because we can look at those carbon dioxide molecules and see where they were coming from. So we know that humans have been changing this, and because we've been changing what the atmosphere is made of, we start to change the climate. And we've known that carbon dioxide can change our climate for over 150 years. Okay, back in 1856, a scientist called Eunice Foote said an atmosphere of that gas, she was talking about carbon dioxide, would give to our Earth a high temperature. And so other scientists in later years independently also saw the same thing. Doubling the amount of carbon dioxide would raise our surface temperature. And John Tyndall in the 1850s also said that the result is a tendency to accumulate heat at the surface of the planet. So this is really well known in the scientific community, that carbon dioxide can make our planet warmer. And what I'm personally really interested in is how this warmer planet changes precipitation and our water cycle. So this is a nice cartoon of our water cycle as a whole. So we can see evaporation from things like the ocean or lakes. We can see that water vapor turning into clouds. We can see precipitation. And we can see transportation, so clouds can move and rain somewhere else, like over the mountains. We can get snow and snow melting, water going into the ground, rivers, all of these things combined. And I'm really going to focus on this precipitation part because that's the part that I'm most excited about. So we measure precipitation in lots of different ways. The traditional way is by using a rain gauge. So there's two different types of rain gauges here. You can kind of think of them as a big bucket, and it literally collects the rain, and you can either measure it automatically or you can manually and essentially use a ruler to measure how much rainfall has fallen. And these are really great, but they don't tell us the rain everywhere. So we can also look at rainfall from things like radars. So we can estimate rainfall from radars that cover across the US and across other parts of the globe, but still they don't really tell us about the ocean, about rain over the ocean, and they don't tell us anything in places where we don't have radars. So a lot of the world does not have radar coverage like the United States does. So we also use satellites in space that emit all kinds of quantities about the Earth. And one of those things they can measure is actually precipitation. So this gives us a nice historical record of how precipitation changes across the globe, or how it has been changing. So I'm not only interested in just the average amount of precipitation, but I'm interested in extreme precipitation, so really heavy rainfall. And this is one example of that. So we've been looking at 2-week periods of really extreme rainfall and how often they've been happening across the US. And this graph is showing years, so from 1981 to 2018, and how many of these really extreme events we have in different parts of the US. So you can see there were some years in the beginning where we might be having 8 of these a year, but more recently we've been getting 8 to 12 of these events per year. So this is another way of showing us that our precipitation has been changing because our climate and our temperatures have been changing. And one other cool thing we can do with data like this is not just look at the rainfall, but look at the impacts that they're having. So in these really heavy rainfall periods, we can look at different storm reports and see what else is happening, as well as just rainfall. And so this is, for an example, from the Southeast United States. And when we had these really heavy rainfall events, there was also a lot of wind, there were tornadoes, there was flash flood and lightning, hail, lots more wind, heavy rain. Sometimes there was a winter storm. Sometimes there was, this rain came in the middle of a drought, as well as hurricanes. So we can really start to understand why this was coming. That helps us be able to predict it better. So this is great to understand what's happened in the past, because understanding why things have happened can help us understand the future. We need a way to make a prediction or a projection of the future. And in climate science, we use what's called a climate model to do that. And this isn't like a model airplane. This is actually a computer model. So those computer code that we use to build apps and build video games, we can use that same code to model how the atmosphere moves. And so this code is huge. I mean, we can have thousands and thousands and millions of lines of code in these models, and it takes supercomputers to run these climate models. Okay. So these climate models divide up the globe into little boxes, and it makes projections of the climate in each of those little boxes. And these models have been the key for climate policy and decisions for the last 5 decades. And the same kind of models and the same kind of equations that describe how the atmosphere moves that we use in our weather forecast models that we see kind of every day telling us what our forecast is going to be for the next few days. These are just kind of on a much bigger scale. So these models, they're calculating things like temperature, moisture, wind, the pressure on every one of these little boxes, every kind of 10 to 20 minutes over 100 years. So it's like trying to do all these little calculations at 70 million points. It's like having 2.5 million Rubik's Cubes and having to do a calculation on every single one of those squares on that Rubik's Cube. And that's why we have to use supercomputers to do them. It would just take a really long time. It would be impossible to do it by hand, and it would take a really long time to do it in just your own laptop or computer at home. But these models can then tell us what the future might look like. And that's what really helps us understand how human activity, like changing greenhouse gas emissions, is affecting our climate. So I use these models a lot, pretty much every day in the work that I do to try and understand how rainfall is changing. So we can use these climate models to look at how precipitation is going to change in the future. So this is a map of the globe. So we can see North America right here. And when you see the blue colors, it's showing that it's going to be getting wetter over the next 100 years. And where you see the orangey colors, it's showing where it's going to get drier over the next 100 years. So across the US, we can see a difference between what's happening in the north, where it's blue, and it's going to be getting wetter, and in the south and the southwest, where it's orangey colors, where it's going to be getting drier. And where you see all these little dots on the screen, that's showing where all these different climate models agree that it's going to be getting wetter or drier. So we can see some other really important changes happening across the globe, like it getting drier in the Caribbean and in parts of the Amazon, where the Amazon rainforest is. And we can see parts of the tropics near the equator and across places like India and Indonesia, where it's going to be getting wetter in the future. And this is really important if we're trying to make long-term plans for our water and our water resources to know what that trend or that change is going to be. But I'm also really interested in how much rainfall varies. So how much are we going to be flip-flopping between wet conditions and dry conditions? Are we going to be changing really quickly, or are we going to be staying in one state for a long time? So what this other image here shows is how rainfall variability is going to change in the future. So now with blue colors, it means it's going to be getting more variable in the future. So you're going to get lots of changes between wet and dry conditions pretty quickly. And where you see oranges or browns, which you don't really see very many of on this map of the future, it would be getting less variable. So what this shows us is across most of the globe, no matter if it's getting wetter or drier in the future, rainfall is going to be more variable. And that might make it harder to forecast, and that might make it harder to plan for your water resources, for things like river flow and various other things. So it's really important to not just understand how the mean is changing, but also how things are going to vary in the future. So when we think about rainfall or precipitation getting more variable in the future, we think that this might be impacting droughts, so long periods of dry conditions, and what we call pluvials, which are kind of like the opposite of drought, when you get a really wet period for a while. And so this is looking at how the number of these events and the length of these events is going to be changing in the future. So on this top left panel, it tells us the change in the number of drought events in the future. So when you see brown colors, it's saying there's more drought in the future. And this looks pretty similar to what we saw in the rainfall. more drought in the South and Southwest US, the Caribbean, parts of the Amazon basin, and extending up towards Europe. But the blue colors show less drought. So maybe this is good for parts of Canada, where they'll be getting less drought in the future. And on the bottom panel, we see how long these droughts are going to be. So when it's brown, like in the Caribbean and parts of the Southwest US, not only are we getting more droughts, but those droughts are lasting longer. So again, this could be really challenging in terms of water and agriculture and various other things that rely on rainfall. But on the flip side, we can look at these wet events. So here, this is the number of wet events in the future. And where it's blue, we see more wet events. So a lot of the northern parts of the US and Canada are going to be getting a lot more wet events, whereas the Southwest is going to get fewer. And we can see this same pattern across much of the globe. And again, when we think about the length of these events, these wet periods are going to be longer as well. So it's really important to think about both sides of this challenge, the times where we don't have enough water and the times when we might have too much, because they both cause really huge impacts, but they have different types of impacts and different ways we need to plan for that. So thinking about the planning, I work a lot with community partners. So people out there in the field who are doing work related to rainfall. So people like water resource managers, emergency managers, and tribal environmental professionals. And we do this because it's really important for researchers and decision makers, people doing work in the field, to understand each other and understand the sort of information we can create and the sort of information that they need. So we hold workshops with these communities regularly. Here are some nice pictures from one of our workshops a few years ago, when we ask them questions like, what does extreme rainfall mean to you? What kind of forecast would you like to have? What would be useful for you when you're making decisions? When do you need that information by? And how do you use that information when you have it? And we've really learned that uncertainty is really challenging, right? We're never going to have perfect forecast and one answer, especially when we're thinking about projections of the future. We always have a range. Some of our emergency managers, they planned for the worst case scenario. They wanted to know what was the worst possible outcome because that's what they wanted to plan for. But other people just wanted to know the most likely so that they could plan for what was most likely going to happen. And here we are sitting down, here's me in the middle, talking to our decision makers and going through kind of their decision-making process of how certain do you need to be to make a decision, like moving resources or opening a reservoir or moving water around or moving people. It's a really challenging thing to have to do when you're working with people in this kind of way. So another way that I use this precipitation information in terms of impacts is to look at how changing rainfall impacts rivers and ecosystems. And one particular project I have in Texas is to look at 2 specific rivers in Texas and look at how changing rainfall impacts the flow of the river and then how this might impact mussel species. So here's a picture of some of these mussels that are really threatened. They might be added to the endangered species list, but they help filter the water in the river. They help keep rivers healthy. So we want to have these animals, these creatures in the river, and climate change and these changing precipitation might be leading to environments where they can't survive anymore. And just one example of that is looking in the San Saba River near Texas. This is showing how often the river is going to be below a healthy flow level. We call this subsistence flow. So how much more is it going to have these really unhealthy flow levels in the future? And we can look at different seasons. So we have winter, spring, summer, and fall. And we can look at different scenarios. So different amounts of greenhouse gases being added to the environment. So the red color is really the worst case. And the green color is almost the best case scenario. If we stop emitting now, what will happen? So in about 50 years from now, in the worst case scenario, we start to see 50 to 60 more days per year or days per season when the river is too low to maintain a healthy system. So this is potentially really going to be damaging for those mussels and the other species in the river that are trying to survive. So what I'm continuing to do now is really continue to understand our climate, how it changes, and doing that in a way that is useful to the people making decisions, right? And this is called actionable science. We want to do science that people use and people can use in their jobs to help improve the environment, the ecosystem, people's lives. And so some of the other projects I'm working on are things called weather whiplash. So those really rapid changes between wet and dry conditions. Also things like, how do we predict the start and end of a wet season? I also look at rainfall in the tropics a lot, which I haven't spoke about here. And even more topics outside of this. There's always more to learn. And there's always more to help share with people using this information. So with that, I will thank you and we can answer some questions.
Wow. Well, first and foremost, I wanted to thank you for sharing all of those visuals. Climate change tends to be a hard topic for students to grasp because you can't actually see it. You can feel some of it. And I just loved all of those graphics and data sets and the images that you use, because I really think it's going to help a lot of students understand this complex topic. So I just thank you for sharing that with us.
Good, thank you.
Yeah, and I love that point of actionable science. We do know that this is one of those topics, it's a little, you have to have some buy-in. So with our students, a lot of this is going to be impacting them in the future more directly than, say, us. So what advice would you give a student that is interested in learning more about climate change?
So I think it's really important to start learning about how climate change is impacting where you live, right? And you can do this in lots of different ways. You could do this by getting a rain gauge and putting it somewhere near where you live and starting to measure it yourself, right? And starting to write down those numbers and track that kind of information. I also suggest that you can reach out to places like NOAA. So NOAA is the National Oceanographic and Atmospheric Administration, and they have a lot of really great resources specifically for the classroom, for kids, for young kids, for people in high school and college to really learn more about the science of climate change, as well as some of the impacts. Places like NASA have the same kind of resources too. And I'd also suggest just talk to people, talk to adults about what they've been experiencing. Have they seen any changes since they've been living where they've been living? Do they see anything that's different? And just talking about it more is really, really important.
So something that, on top of what you just said about adults, I live in Florida, so I have experienced over my lifetime, not necessarily more hurricanes, but stronger and more detrimental as far as rainfall goes. Is there a correlation between climate change events and intensity of those storms?
Yes, so there has been some evidence suggesting that as the climate has been changing, certainly when we get hurricanes, they've been more intense, but they have definitely had a lot more rainfall. And that is because when the air is warmer, air is able to hold more water inside it. So as we increase the temperature of the Earth, there's physically more water in the air. So when you get something like a hurricane, there's more water vapor inside it, so that when it does rain, there's more water coming down. And we know that in hurricanes, a lot of the damage and the deaths tend to occur from water, right? Flooding and storm surge rather than the wind. Yeah, the water is really damaging and important to understand.
Yeah, and so on the flip side of that question, and a lot of our students that are going to be watching are in California, and there's definite drought and wildfire concerns. So same kind of question, but can you relate it to those wildfires?
Yeah, so drought is really a similar challenge, but on the opposite end, right? So if the air can hold more water, it means that more and more water vapor can get into the air, but it might be longer until it rains next time. Because previously you might just put a little bit of water vapor in and it gets too much and it rains. But now, because the air can hold more water vapor, it takes longer between rainfall events. And because it's warmer, we can get more evaporation. So the soils get drier and the plants don't get enough moisture and the plants can't grow. So if the plants die, then that's fuel for those fires that could be sparked by natural things like lightning when there is a storm, but also by wind events that can knock over power lines. And that can make our fires larger, more dangerous. But also populations have been changing and we've been building more and more houses and environments near where that vegetation is, right? Going into those forest lines. So there's more people potentially in dangerous situations where if there is a fire, they may not have much time to move. There's more houses, more money in some of these places. So we get larger damages from the fires that do happen.
Thank you for that. Yeah, I just wanted to kind of hit the two ends of the spectrum because I know I've heard like, well, it's still doing this and it's doing that. Well, it's all related to each other, right? It's just one big sphere that we're living in and it's all related. So bring this question.
Yes, always. We're all connected.
Thank you so much for sharing all that information with our students and with all of our people that are going to be watching this. I know this is an important topic, so I really appreciate you taking the time to share your knowledge with us and give us a new perspective on climate change.
Thank you so much for having me.
So if you would like to potentially do your own research investigation on climate change, we do have our Spring Research Experience program available for registration right now. So you can go ahead and visit our website and learn more about our research programs. And if you have any direct questions about this talk or any of our other programs, you can email me at jen@headwaterscienceinstitute.org. So thank you again, Elinor, and thank you everybody for joining us today. Make sure you check out the activity if you want to do your own investigation on climate change. Want to learn more about our Lunch with the Scientists program? Make sure to like and subscribe and visit us online at www.headwaterscienceinstitute.org for a full list of our video library and curriculum.